Hello, welcome to lecture 19 of Elec NH2CI5. In this lecture, we'll discuss how we can connect capacitors and inductors to create combinations of these elements. We'll see that inductors follow the same laws governing resistors, while capacitors, they need a different type of treatment. So I will show you this through a number of examples, and we'll take it from there. Okay, before I start discussing the combination, I just want to review the laws governing capacitors and inductors, just to put them together in the same slide. So as you can see here, we discussed before the capacitor, we said that the capacitor accumulates charge, and this charge represents voltage across it. We call this voltage VC. The current going through the capacitor is considered positive if it flows from the positive electrode to the negative electrode. So it flows from the positive voltage to the negative voltage. IC is considered positive here. So when the capacitor is charging, IC is flowing this way, and the charge across these plates are increasing, and the voltage is increasing. If the current flows in the opposite direction, so it flows from positive to negative through the circuit, then the capacitor is discharging and the current is considered negative. So this is the direction of the positive current. The opposite direction, the one pointing from positive to negative through the circuit, is considered negative. Okay, so this direction here is our reference direction. A current is considered positive if it flows from the positive plate to the negative plate, from the higher voltage to the lower voltage. The expression of the current in terms of the voltage, the current is proportional to the derivative of the voltage. IC is equal to C dVC by dt. And you shouldn't get confused that I use here IC small letter and IC capital letter. I mean effectively the same thing here. It is the capacitor current IC. The capacitor voltage is obtained as an integral of the capacitor current. So we integrate IC from minus infinity to t, and as I explained in class, this integral here represents the total charge accumulating. So this one is Q of t. So if you divide Q of t by C, you get Vc of t, because the relationship between the charge and the capacitance and the voltage is that Q is equal to CV. The voltage across the capacitor is always continuous. The voltage cannot see an abrupt change. It cannot change from 5 to 1 in the same second, in the same time. This can't happen. It has to be always continuous. At DC, it represents the open circuit. The reason for this, if you take a look at this equation, you see that at DC, everything is at steady state. Nothing is changing. It's DC. Then dVC by dt will be 0 because nothing is changing with time. If this derivative is 0, this means that the current will be 0. And if you have something that draws 0 current, this means that it represents open circuit. So when you analyze a DC circuit with capacitors in it, you replace these capacitors by open circuit. The energy stored inside the capacitor at any time is 1/2 multiplied by the capacitance by the voltage squared. Inductors, it is the opposite. The current takes the position of the voltage, and the voltage takes the position of the current. So this is the reference. This is the positive direction of the current. It's flowing from positive terminal to the negative terminal. This is the voltage here. The voltage is the derivative, is proportional to the derivative of the current, which is opposite to the integral here, and the current is proportional to the integral of the voltage, which is opposite to the difference here, or the differentiation here. As I explained again, the same notation will apply. The inductor current is positive if the current is flowing from the positive terminal to the negative terminal, so we assume certain polarity. The current will be negative if it's flowing in the opposite direction. Okay, current here has to be continuous. Current cannot be discontinuous in an inductor. So the current cannot change suddenly from 1 to -1. This can't happen, but the voltage can be discontinuous. And the reason for this, if the current is discontinuous, then this derivative will be infinite. And if this is infinite, this means that you need an infinite voltage to create this change. And this is not really something physical. So this current has to change in a continuous way. Energy, and at the last thing I want to mention, or the one for last, that at DC, an inductor represents short circuit. The reason is, if you take a look here at DC, means nothing's changing with time. Then the derivative of the current relative to time is 0, which means that the voltage across the inductor is 0. When you have something with 0 voltage across it, this means it's short circuit. So at a DC circuit, you replace the inductor by a short circuit, you replace a capacitor by an open circuit. Lastly, the energy stored in an inductor is 1/2 L multiplied by the value of the current squared. Now we'll connect inductors in series and the inductors in parallel, and let's see how we can replace, as we did before for resistors, how we can replace a number of inductors connected in series by one single inductor, and replace a number of inductors connected in parallel by one single inductor. So here, when you connect them in series, each one of them will have its own voltage drop. So this is V1, this is V2, this is V3 up to Vn. This is the inductance L1, L2, L3 up to Ln. The same current is flowing in all of them. Then KVL still applies here. KVL will apply it every time, at every single time instant. So we can simply say at any time instant V is equal to V1 of t plus V2 of t plus V3 of t up to Vn of t. I can replace each voltage by its corresponding inductance multiplied by the derivative of the current. Okay, but remember, it's the same currents flowing in all of them because they are in series. So the same charges are flowing through all of them. So this is di1 by dt is di by dt, di2 by dt is di by dt, and so on. So I can take di by dt out, and then I will have here L, the first inductance, plus the second inductance up to the nth inductance. So this looks like it is the voltage is equal to an equivalent inductance, L equivalent, multiplying by the derivative of the current. So this is the equation governing an inductance, and the value of this inductance is the sum of all the other inductances. So whenever you see inductances connected in series in this way, you can simply replace them by one single inductance. Okay, it's called L equivalent. Okay, it has the same voltage V and the same current I going through it. Okay, the same current I, and the value of this L equivalent is simply, this L equivalent here is the sum of all the other inductances that you have. So this is exactly what we did for resistances. We say if we connect a number of resistances in series, then the equivalent resistance is the sum of all resistances. This is a nice thing about inductances. They follow exactly the same laws like resistances. Okay, so this for series connection. So if you see any number of inductors connected in series, you replace them by one inductance whose value is the sum of all the inductances. Okay, what happens when you connect the inductances in parallel? So here we have an inductance L1 is connected in parallel with inductance L2 up to inductance Ln. Each one of them has its own voltage V1, V2 up to Vn, but because they are connected in parallel, all these voltages V1, V2 up to Vn are equal to the voltage V. Okay, what is going to be different is the current. The current I will split into I1, I2 up to In. So what you're going to be doing here, in order to replace all these inductances by one single inductance, we're going to write KCL at this node. This is simply one node here. Okay, we agreed if you have short circuit, it's simply one node. So simply that I is equal to I1 plus I2 up to In. But each current is proportional to the integral of its voltage. So I1 is 1 over L1, the integral from minus infinity to t, V1 of tau d tau. I2 is 1 over L2, the integral from minus infinity to t, V of tau d tau, and so on. But remember, all of them have the same voltage because V1 is equal to V2 up to Vn. They are connected in parallel. So we can take this term out. It's a common term. You can take it out. And I wrote it here as minus the integral from, or the integral from minus infinity to t, V of tau d tau. And what is left inside the bracket is 1 over L1, 1 over L2, up to 1 over Ln. But this looks like the expression of the voltage or voltage current expression of one inductor, because for a single inductor, V is equal to 1 over L multiplied by integral from minus infinity to t, V of tau d tau. So this whole thing, I can simply replace it by 1 over L equivalent. Okay, so I replaced 1 over L1 plus 1 over L2 up to 1 over Ln. This is going to give me a number. This number is 1 over L equivalent. This relationship is the relationship of a single inductor. So this combination that I have here, I can simply replace it by just one inductor. Okay, and it has a current I flowing in. It has a voltage V across it, the same voltage V, the same current I. Okay, and the value of this L equivalent, this value here, is given by 1 over L equivalent is equal to 1 over L1 plus 1 over L2 up to 1 over Ln, as you see here. But this is exactly what we did for parallel resistances. We said if you have n resistances connected in parallel, R1, R2 up to Rn, then their equivalent resistance is given by the law 1 over R equivalent is 1 over R1 plus 1 over R2 up to plus 1 over Rn. So this is the nice thing about inductances, they follow exactly the same pattern as resistances. And everything else will be the same for them. You can use Y to delta combination the same way you did it for resistances without any difficulty. It still applies, it still works the same way. Okay, let's take a look at an example here. We have this L combination, combination of inductances, and would like to find the equivalent inductance seen between points A and B. As we agreed, if we have any combination of inductances, we can replace it by only a single inductance, in the same way we did for resistances before. You take a look at this circuit, you don't see really any series or parallel connection. So what you have to do, you have to start by using a Y to delta transformation to break this Y here into delta, and use exactly the same expression that we have for resistances, because inductances follow the same laws, very similar way of it's not exactly the same laws, but I mean when they are connected in series we sum them, when we connect them in parallel we treat them in the same way we treat resistances in parallel. So I'm gonna use a Y to delta connection to break this Y, and this will result in a simpler circuit that we can analyze further. Okay, so I did that. So this was my initial circuit here, 1 Henry, 1 Henry, 1 Henry. If I use the expression for Y, I convert this Y into a delta. So I get 3 resistances, 3 inductances connected in a delta form. You'll find that the value of each one of them is 3 Henry. Okay, go back and use the Y to delta transformation. You'll see that this is 1, 1, 1. Then the 3 delta inductances will be 3 Henry, 3 Henry, and 3 Henry. So now this 3 Henry is in parallel with 6 Henry here. This 3 Henry is in parallel with 6 Henry here. This 3 Henry in parallel with 6 Henry here. We treat them in the same way we treat parallel resistances. So these two in parallel will give me 3 by 6 over 3 plus 6. So you get 18 over 9. So the net of these two will be one inductance of value 2 Henry. These two are exactly the same. 3 in parallel with 6 will give us 3 by 6 over 3 plus 6. The same way we do to the resistances, you get 2 Henry. And in the same way, these two will give us 2 Henry as well. So if you put all this together, you see that this is how your circuit will be reduced to 2 Henry in series with 2 Henry, and this branch is in parallel with another 2 Henry. So the equivalent inductance looking from this side, it is 4 Henry in parallel with 2 Henry. Okay, so it's 2 Henry in parallel with 2 plus 2. So 2 in parallel with 4, so it's 2 by 4 over 2 plus 4. This will give us 8 over 6 Henry, or 1.33 Henry. So you can see what we did, we were able to use laws similar to the series and parallel combination of resistances. For capacitors, the situation is different. And I will show you this in the form after we have one more example on the case of inductances. Okay, let's take a look at this example. We have a number of inductances connected in the shown way. We would like to find the equivalent inductance seen between points A and B. So this point A, this point B. So this whole combination can be replaced by just one inductance of value L equivalent. I would like to find this L equivalent. When you take a look at this circuit, immediately you can see that this inductance and this inductance are in parallel. You can see this is one node and this one node. So you have 12 millihenry in parallel with 12 millihenry. So this will give me 6 millihenry. You see as well that this one and this one share this point here, and at the same time all these 3 points are the same point because they are shorted. So this one and this one, they are also in parallel, and the net combination will be 6 millihenry. So we can simplify the circuit further, combine these two to get one inductance of value 6 millihenry, combine these two to get one inductance of value 6 millihenry. So I drew the circuit again here, and as I said, I'm gonna combine these two, will give me 6 millihenry. So I have this one here. I'm gonna combine these two. This will give me 6 millihenry, and this is what you have here. Now, when you take a look at this circuit, in the way we have with resistances, if a current is flowing into here, it will split into part will go this way and part will go that way. So this branch and this branch, they are in parallel. So you have here 12 millihenry in parallel with 18 millihenry. 12 plus 6. So the net combination of this branch will give me 12 plus 6 millihenry, so 18 millihenry. But this branch is in parallel with 12 millihenry. So you get 12 multiplied by 18 over 12 plus 18. And when you do the calculation, you get it is 6.2 millihenry. Please verify these answers. Okay? And so I replaced all three of these by 6.2 millihenry, and this is in series with this 6 millihenry here. So the equivalent inductance, I didn't show the final answer here. L equivalent here is really will be 13.2 millihenry. Okay? So what you do here, you simply combine them. Combine these two, they are in series in the same way we do with resistances. Okay, for capacitor situation is different. Let's see why is that. We connect a number of capacitors in series. Okay, so the voltage here is V1. This is C1. The voltage across is V1. The current going through it is I1. This is V2. This is voltage V2. It is the voltage across the capacitor C2. The current going through it I2, and so on. The current going through all of them will be the same. So I1 is equal to I2 is equal to I3 is equal to IN, because they are connected in series. Okay? But the voltage V, if you apply KVL, you see that V of t, which is the voltage here between these two terminals, is equal to V1 plus V2 up to Vn. So we start with this one. This is KVL. V is equal to V1 plus V2 up to KVL. I'm missing here a plus sign here. Okay, so the different part here is that you are going to replace each voltage by 1 over C1, the integral from minus infinity to t I1 of tau d tau. So V1 is replaced by 1 over C1, the integral from minus infinity to t I1 of tau d tau. V2 is going to be replaced by 1 over C2, the integral from minus infinity to t I2 of tau d tau, and so on. And Vn, you replace it by 1 over Cn, the integral of its current d tau. But remember, all these currents are the same. So I1 of tau is equal to I2 of tau is equal to I3 of tau up to In of tau at all time tau. Because this is series connection, so the same current flows through all of them. Okay? So I can take this integral out as a common term. And now the surprising thing is, you'll see that what is left inside is 1 over C1 plus 1 over C2 plus over 1 Cn. The equation governing a capacitor is that the voltage is 1 over the capacitance multiplying the integral of the current. So I'm going to replace all this bracket here by something called 1 over C equivalent. And this will be multiplied by the same integral of the current. So what happens here, I was able to replace all these capacitances in series by a single capacitance. But this capacitance is not their sum. I'm actually getting it by the expression 1 over C equivalent is equal to 1 over C1 plus 1 over C2 up to 1 over Cn. So, and this is the same expression we have for resistances in parallel. Okay? So this is a fundamental difference from the inductance case. When you connect capacitors in series, we use the same law we use for resistors in parallel. Okay? So all these things connected in parallel, I can simply replace them by connected in series. I can replace them by a single capacitor. This is called C equivalent. Okay, it will have the same current going through it I. It will have the same total voltage V of t across it. Okay, but the only difference is that this C equivalent is obtained from the relationship 1 over C equivalent is 1 over C1 plus 1 over C2 up to 1 over Cn. Okay. So this is a fundamental difference. And one other thing to notice is that if there is the charge is going to be the same across all of them. So you have here a charge Q minus Q on the positive electrode minus Q here. You get Q minus Q. You get here Q minus Q, and so on. So the netted charge is equivalent to really a charge of value Q on this positive electrode here, the same charge actually, okay, plus here to this Q, and negative Q here on this negative electrode. Okay, so keep in mind, to summarize what I'm saying here, if you connect capacitors in series, treat them in the same way you treat resistances in parallel. Okay, they have the same current going through all of them. The voltage across them is simply the sum of all the voltages, but this means you're going to use the parallel expression for the resistances. Now we move to discuss how we're going to put capacitors in parallel. What if you want to put capacitors in parallel? If you put capacitors in parallel, then they all share the same voltage. So V1 is equal to V2 is equal up to Vn at any time t. At any time t. Because now we're talking about transient analysis, not DC anymore. So at any time t they are equal, and they are equal to this voltage V of t. The current flowing in I of t is the one that's going to be split into a current I1 go through the capacitor C1, current I2 will go through the capacitor C2, and so on up to IN, the capacitor Cn. So what we can do here, as we did for inductors, we apply KCL at this node. Current flowing in is equal to the sum of all the currents flowing out. So I of t is equal to I1 of t plus I of t up to IN of t. Now we know that from a study of capacitors that the current flowing through the capacitor is proportional to the rate of change of the voltage. So I1 is C1 dV1 by dt. V1 is the voltage across the first capacitor. I2 is C2 dV2 by dt, where V2 is the voltage across the second capacitor, and so on. Now, all these voltages are the same because they are in parallel. So V1 is equal to V2 up to Vn. So I can take this dV by dt out as a common term. Okay, then I know, I can see what is left inside is C1 plus C2 up to Cn. I'm going to replace this sum by C equivalent. Okay, and I can simply write it there that I of t is equal to C equivalent dV. I don't have to put Vn here. It is dV of t by dt. So these capacitors who are connected in parallel, they look like one capacitor because this is the equation of a capacitance. And the value of this capacitance is their sum. C1 plus C2 up to Cn. Okay? And this is surprising. So this is very different from the case of resistors. So when you connect the capacitors in parallel, you use the same law you use for resistors in series. We add the value of the capacitances. Okay? So you can see C equivalent C1 plus C2 up to Cn. Okay? This is very interesting. Notice that each one of them is storing a different charge. This one is storing a charge Q1, storing a charge Q2. They can really accumulate lots of charge through creating a bank of parallel connected capacitors. Okay, but of course the current going through each one of them is different. The voltage across them is the same. Let's consider the first example. We would like to select the value of the capacitor C here, so this C and this C, such that the total capacitance seen between these two terminals is equal to 1 microfarad. This is given as 1 micron, this is 2 micron, this 1 micron, this 1 micron, okay? So we'd like to choose the value of the capacitance C such that the total capacitance will be equal to 1 microfarad. Now, let's take a look at the circuit, try to see if we can simplify it further. We see that this 1 microfarad is in parallel with this 2 microfarad. You can see they share this node and this node. So their net is equal to 3 microfarad. We have to add them. Capacitors that are connected in parallel, they added in the same way we add resistors in series. Now let's take a look at this one. This is 1 microfarad in parallel with the capacitance C. Then the net capacitance of these two is 1 microfarad plus C. Okay, so just to keep this one in mind. So this is the first thing I'm going to be doing. This will be 1 microfarad plus C, and these two will be 3 microfarad, and I end up only with one branch in parallel with another branch. So I redrew the circuit here, and then I combine 2 microfarad in parallel with 1 microfarad will give me 3 microfarad. This capacitance is still the same. 1 microfarad in parallel with C, I wrote it as 1 microfarad plus C. So I'm here assuming that the value of C will be in microfarad, okay? So this has to be very clear. If I write this as 1 plus C microfarad, this means that C will be in microfarad. What is the equivalent resistance now? What is the equivalent resistance? Take a look from this side. It is simply this branch in parallel with this branch. But what is the capacitance of this branch? These are two capacitances connected in series. And when we connect two capacitances in series, we treat them like resistors in parallel. So the equivalent capacitance of these two will be C multiplying 3 over C plus 3, and the answer will be in microfarad. Okay? Now, what about these two? These, again, are two capacitances connected in series. So I will use the same law I used for resistances in parallel. Okay? So this will give me 1 plus C multiplying 1 over 1 plus C plus 1. So you get this expression here. And remember here, I started to assume that C is in microfarad. So this whole answer will be in microfarad. So if the answer of C is 0.5, it means it's 0.5 microfarad. Okay? And because this branch is in parallel with this branch, the net capacitance is the capacitance of this branch plus the capacitance of this branch. When we put two capacitances in parallel, we sum them. We treat them like resistors in series. And this is why I use this plus sign here. So this is the capacitance of the first branch, this is the capacitance of the second branch, and they are connected in parallel, and this is why I add them. Now, my target is to find C that will give me an equivalent capacitance of 1 microfarad. So let's find the equivalent capacitance here. Let's take a common denominator. We multiply this one here by 2 plus C. We multiply this one here by 3 plus C, okay? And we combine all the terms that we are going to get. I combined all the terms. I collected the different coefficients here. Of course, I can simplify it further. So 3C squared plus C squared can give me 4C squared, and so on. I want to add, this is the equivalent capacitance, and this is the equivalent capacitance in microfarad. I'm repeating this again. I already made the assumption that the answer is in microfarad, and C will be in microfarad. So this will be equal to 1. You shouldn't be putting 1 10 to the minus 6. It's just 1. Because in all my calculations, I assumed that the result will be in microfarad. So if you put this one, and then you multiply this denominator here, and then you collect all the terms to one side. So 3C squared plus C squared minus C squared will give you 3C squared. 6C plus 4C minus 5C will give you 5C. Here you have plus 3, and you get minus 6 from the other side, you get minus 3. Okay? If you divide both sides by 3 just to make the coefficient of C squared 1, this is what you get. You apply the law for solving quadratic equation, you'll get two answers. One of them has to be rejected because the capacitance has to be positive, so you keep only the positive sign, and the answer here for this case is 0.468 microfarad. So the capacitance has to be equal to 0.468 microfarad in order to get a total input capacitance of 1 microfarad for this combination. The conclusion of this example is, if you connect the capacitors in series, you treat them like resistors in parallel. If you connect the capacitors in parallel, you treat them like resistors in series. Let's consider one final example here. We have a circuit. This switch S has two positions. First it's opened, and then it is closed. So when it is opened, this C is not part of the circuit. It's disconnected. So you have only 1 microfarad, and you have these two in parallel, okay? But if you connect C, if you close the switch, and C will be here, so C will be in parallel with 6 microfarad. So in the first situation, you have 6 microfarad in series with 3 microfarad, okay? This has to be very clear. 2 microfarad in parallel with 1 microfarad will give you 6 microfarad. While here, you have 6 microfarad in parallel with C will give me 6 microfarad plus C, or 6 plus C microfarad. And this 6 plus C microfarad will be in series with this one here, which is 3 microfarad. So let's see what they're asking for us for. They are saying we'd like first to determine V1 of t and V2 of t when the switch is open. So you have V1 is the voltage across these two, across 1 micron and 2 micron, and V2 is the voltage of 6 micron. And later they are saying if the switch is closed, we would like the current I of t, which is the current drawn from the source here, to be equal to has a peak value of 0.25 ampere. Okay, so let's consider the first case. 6 microfarad in parallel with 3 microfarad, and let's handle this one first. So for the first case, this is what we have, 6 microfarad in series with 3 microfarad. This is V1, this is V2. Write the expression for the voltage. This is the source voltage, so the source voltage Vs will be equal to V1 plus V2 at any time t. But V1 is 1 over C1, the integral from minus infinity to t I of tau d tau. V2 is 1 over C2, the integral from minus infinity to t I of tau d tau. Remember that I1 of tau is equal to I2 of tau is equal to I of tau because they are connected in series. This is why I didn't write here I1, I didn't write here I2, because I1 and I2 are the same. Now, notice something very interesting. This term is common. This is V1 and this is V2. So the voltage will be divided between the first capacitance and the second capacitance according to the inverse of the ratios. And this is very different from what we have for the case of the resistors. For the resistors, you say the voltage V1 will be R1 over R1 plus R2 multiplying Vs. Here I don't have R1, I have 1 over C1. Here I don't have R2, I have 1 over C2. It's a voltage divider, but it is with the opposite of the ratio, or it is actually the same expression we use for the current dividers. Because this is what we have here. If I want to write it, I'm going to write the current the voltage division as follows. I'm going to write it as, if I want to get the voltage across the 3 microfarad, I'm going to write it as 1 over 3 over 1 over 3 plus 1 over 6. So if you multiply both sides by 3 by 6, you end up by 6 over 3 plus 6, which is the same current division we used for parallel resistors. Okay, so what is going to happen here? The voltage will be divided with, if I want to get the voltage across the 3 microfarad, the ratio will be 6 over 6 plus 3. Okay, why is that? Because this is the way we used to divide currents in the case of parallel resistors. So as a rule, if you have resistors connected in series, the voltage will be divided between them in the same way we divide currents between parallel resistors. The reason is here R1 has been replaced by 1 over C1. R2 has been replaced by 1 over C2. Okay, so the voltage V1 is 6 over 6 plus 3 multiplying Vs. This 100 sine 1000 t, so this will give me 6 over 9, you multiply by 100, then you get 600 over 9 sine 1000 t. And this will be the value of V1 of t. This is sinusoidal with time, so this one will be sinusoidal with time, this one will be sinusoidal with time. But KVL will apply at every time step. So if you want to see the voltage between here and here, you will see it's equal to this voltage plus this voltage. The voltage across the second capacitor will be obtained exactly the same way. If you want to get the voltage across the 6 microfarad, then the division ratio will be 3 over 3 plus 6. You multiply this by Vs, so you get 300 over 9 sine 1000 t. Now, when you close the switch, the capacitor C will be added to the circuit. So C is in parallel with 6 microfarad. Then I replace them both with one capacitance whose value is 6 plus C microfarad. Here we still have 3 microfarad. Then what is the equivalent capacitance of these two? These are two capacitors connected in series. And when you connect capacitors in series, we use the same expression we use for resistors in parallel. So the equivalent capacitance of these two will be 3 multiplying 6 plus C over 3 plus 6 plus C. And I know here that my answer is in microfarad. Okay, just keep in mind, I didn't include 10 to the minus 6 here, but I know my answer will be in microfarad. So I treat them, as you can see, in the same way I treat resistances in parallel. This is the equivalent capacitance that I'm gonna get in terms of C. C is my unknown. But they are telling us that they want to get a big current of 0.25 amperes. Then I have to write the expression for the current. If I know, if I have a voltage source with this value and it's connected to an equivalent capacitance C equivalent, the current going through the circuit will be C equivalent multiplying by dV by dt. So let's write the expression for the current, and let's try to set its peak to be equal to 0.25 ampere. So the circuit has been reduced really to a voltage source connected to an equivalent capacitance, and this equivalent capacitance, we wrote its expression in the previous slide. So the current going through here from the expression of any capacitor, it is C equivalent dV by dt. So the voltage is 100 multiplied by sine 1000 t. If you differentiate sine 1000 t, you get 1000 cosine 1000 t, and this is the amplitude of the voltage source. So this will give me 10 to the power 5. This will give you 10 to the power 5 multiplied C equivalent cosine 1000 t. This is the amplitude of the current. So the current is a cosine waveform, and it oscillates with a peak value of 10 to the power 5 C equivalent. So what you have to do now, you have to equate this number, which is 10 to the power 5 C equivalent, to 0.25. Okay, and or I can simply write it that I can divide this one by 10 to the power 5. This becomes 10 to the minus 5. I can take also 10 to the minus 1 and write this one as 2.5 microfarad to be equal to C equivalent. Why do I write it this way? Because I have already C equivalent in microfarad. It is 3C plus 18 over C plus 9. So I'm going to equate 3C plus 18 over C plus 9 to 2.5, not 2.5 multiplied 10 to the minus 6, okay? Because I know that this already is in microfarad. If you multiply both sides by 2.5 and you collect all the coefficients, you'll be able to see that C is equal to 9 microfarad. Okay? So the conclusion is from all this discussion, if you connect capacitors in series, we treat them like resistors in parallel. If you connect capacitors in parallel, we treat them like resistors in series. If you have capacitors connected in series, the voltage is divided between them in the same way we divide the current between resistors in parallel. Okay? And of course we can get all type of circuits and calculate the currents and so on, and once we replaced any circuit by its equivalent capacitance, this will be the equation governing the current and the voltage, and this will be the value of the C equivalent that we have.